Every single time you click a mouse, type a letter, or launch an app, literally billions of things are happening inside your computer's processor. But what's keeping all that chaos in order? Well, today we're diving deep into the unsung hero of the CPU, the control unit.
Just think about it for a second. Your CPU has all these different parts, right? You've got the part that does the math, you've got temporary storage spots, you've got access to the main memory. But what's telling the math unit which numbers to add and where to find them? What's making sure everything happens in the exact right sequence? That's the real puzzle, isn't it?
The best way to picture the control unit is to think of it as the conductor of a huge orchestra. It doesn't actually play an instrument itself. It's not the one crunching the numbers. Nope. Instead, it stands at the front, waving its baton, telling the violins when to come in, the brass when to play loud. It directs the flow of data between all the other parts, making sure everyone plays their part at the perfect moment.
And here's the more, textbook definition. It's the part of the CPU that directs the whole operation. It takes the program's instructions and basically translates them into signals that tell the memory, the math unit, and everything else what to do. It is, without a doubt, the ultimate middle manager of the CPU.
All right, so what's our game plan? We've just met our orchestra conductor. Next, we're going to look at the simple 4-step rhythm it follows for absolutely everything. Then we'll get into the 2 main ways you can build one of these things. We'll dive into the details of the more flexible method, and we'll finish up with the classic showdown, speed versus flexibility.
So we know the control unit is a conductor, but what music is it actually reading from? Well, it turns out every single thing your computer does, from moving the cursor to loading a web page, follows this constant 4-step beat. It's called the instruction cycle.
It's this super simple but super powerful 4-step recipe. First, it has to fetch the next instruction from memory. Then it decodes it. It looks at the instruction and goes, okay, what on earth does this string of 1s and 0s want me to do? Next, it sends out the signals to execute the command, maybe telling the math unit to add something. And finally, it makes sure the result gets stored back where it belongs. Fetch, decode, execute, store. Over and over and over again, billions of times every second.
And if we look at a diagram like this, you can see the control unit is right there, smack in the middle of everything. See how it takes in 2 key things? It gets the instruction it needs to work on, and it gets that steady tick-tock from the system clock to keep the whole orchestra in sync. And what does it send out? A whole stream of control signals, the actual orders for the rest of the CPU.
Okay, so we've got a handle on what it does. But how do you actually build a control unit? Well, it turns out there are 2 totally different ways to do it, 2 different design blueprints. And the choice between them has massive consequences for how that processor is going to perform.
So on one side, you have the hardwired approach. Think of this like a custom-built machine, where all the logic is physically burned into the circuits. On the other side, you've got the microprogrammed approach. This one is more like having a tiny, simple computer inside the control unit, and it runs its own little program to figure out what to do. It's a classic hardware versus software battle, right at the heart of the CPU. Let's look closer at the hardwired design first. An instruction comes in, it zips through a fixed maze of logic gates and decoders, and boom, a control signal pops out the other side. Because it's all physical hardware, it is incredibly, ridiculously fast. But what's the catch? If you ever want to add a new type of instruction, you have to redesign the entire chip from scratch. It's blazingly fast, but totally inflexible. It's a specialist tool built for one job. So, what about that other, more adaptable approach? If a microprogrammed unit is kind of like a tiny computer running its own software, what are its moving parts? How does it actually read its sheet music? Well, it all starts with something called a micro instruction. So you know how a programmer might write a big command like add 2 numbers? For the CPU, that one big command gets broken down into a bunch of tiny, fundamental little steps. These tiny steps, things like move data from this register to the math unit or open this data pathway, those are the micro instructions. They're the absolute smallest building blocks of an operation. And where do all these tiny instructions live? They're stored in a special, super fast little bit of memory right inside the control unit called, you guessed it, control memory. This is basically the software, the script for our little computer within a computer. And this is the game changer. Because it's software, you can change it. That's what gives this design its amazing flexibility. Okay, so we've got our script, the microprogram, sitting there in the control memory. But what's actually reading it line by line? That's the job of the sequencer. Its only job is to figure out the address of the very next micro instruction to run.
It's the little guy who's constantly turning the page of our sheet music, keeping the performance moving forward.
But this sequencer is way smarter than just reading line 1, then line 2, then line 3. It's got some real logic built in. Sure, it can just increment to the next instruction, but it can also branch. It can make decisions. It's like an if-then statement. It can check on the status of the last calculation and jump to a different part of the microprogram. It also knows how to take a big instruction and find the right starting point for its microroutine. It can even handle subroutines. This is what makes it so powerful.
So now we have our two competing designs on the table. You've got the rigid but lightning-fast hardwired unit, and you've got the slower but super adaptable microprogrammed unit. And this brings us right to the heart of a classic engineering dilemma.
And this table really just lays it all out, doesn't it? When it comes to pure speed, hardwired wins, hands down, no contest. But microprogrammed wins on pretty much everything else: flexibility, ease of design, and cost. I mean, if you want to add a new instruction to a hardwired CPU, you're literally designing a new chip. With a microprogrammed one, you just update its software. This choice has a huge impact on the chips we all use every day.
So really, the whole thing boils down to this. Are you trying to build a processor that needs to do a few things as fast as humanly possible? You're going to go hardwired. Or do you need a processor that can handle a whole bunch of complex instructions, one that's easier to design and can even be updated later? Well, then microprogrammed is your answer. It's the ultimate choice between a super fast specialist and a slower but much more adaptable generalist. And that leaves us with one last question to chew on. Modern CPUs, they're just unbelievably complex. They have to be insanely fast, but they also have to handle this huge, constantly evolving list of instructions. So, given these two very different approaches, how do you think